What I want to do today is talk about energy. So, before I talk about energy, I want to remind you that the first zeroth law stated that a change in position is equal to speed, average speed we found to be, times change in time. And that the second zeroth law, delta V equals A delta T. And these two things came together to give us the zeroth law theorem. So when I set those two time intervals equal to one another, because the time it took to change the speed was the same as the time it took to change the position, we got sped English. Oh well, it's physics class. ADS equals V bar dV. And we use that a couple of times, and we'll use it more in the future as we move forward. All right? But that's just kinematics. And so we've been on force for a while now, and that's dynamics. That's the cause of motion. Forces produce changes in speed, or accelerations, if you will. Accelerations are due to forces. Well, we were just talking about the Atwood machine, and we've been talking about inclined planes, and it's always the mass of an object under the force of gravity. Well, it's not always that, but so far a lot of the motion has been due to allowing a mass or a differential mass to work under the influence of gravity, and that produces a change in speed and position. And so in these systems that have acceleration, changing positions, changing speeds, and average speeds, there's always some sort of mass involved. And so I can just put it in here as a constant. All right? That color doesn't show up so good on screen, so let me change colors. That's a little better. So mass. I want you to think about mass differently than you're used to. Mass isn't just how much stuff is in an object. It is that too. It's the number of atoms, Avogadro's number and molar mass, and you can go through all of that, density, volume, etc. But from a physics standpoint, a more comprehensive view of mass is it's a measure of its inertia. All right, so that was Newton's first law about how an object at rest or in motion will stay that way unless acted upon by an outside force. We call that inertia. Inertia is a property of an object to resist a change in motion. Okay? So if we wanted to, and we do, we could just kind of write in here mass. I need to change the size of that. Mass is a measure of an object's inertia, which is the property of an object to resist a change in motion. That's what mass is, if you wanted to be clear. So mass is a measure of an object's inertia. All right? Well, what does that do for us in terms of energy? Well, I'm hoping that you recognize that MA, what is MA? According to Newton. Force. All right, so that's force. So I could change this description to force times basically distance, if you will, or displacement, equals mv bar delta v. Well, m times basically 1/2 of V plus V naught times V minus V naught. Hopefully you recognize that that V plus V naught times V minus V naught is going to end up being a difference of perfect squares. That's why we made you take algebra before you took this course. So in the end here, we get that right there. Force times displacement equals 1/2 the mass times the difference of the squared speeds, final and initial. And so if the initial speed was 0, you just get 1/2 mv squared, which is a pretty common description of something called kinetic energy. So let's give some attention here to this. First things first. Force times distance. It takes a force applied. So, we have these rolling chairs. If I apply a force to the chair that's large enough, it will displace that chair. If you had a job pushing chairs around, you would call that work. And if the chairs were heavy, you would call it heavy work. All right? Or pushing boxes around, or pushing you name it around. Okay? Forces that produce displacements of objects, we naturally call that work. I worked hard today, pushing chairs around, okay? Or whatever. Okay? So we call it work. And we use the symbol capital W for work. For once, every now and then we actually make the letter match the idea and the word that goes with it. So we call that work, forces producing displacement. Now, one important idea that will soon become more evident in the example that follows this is a potential kind of energy. Okay? So for instance, an object that is, if I was holding an object, say a bottle of water, you can feel it when you hold something up in the air. You can feel its weight. Where's that weight coming from? It's coming from the earth. For some reason, this thing weighs, I feel it, its weight, and if I let go, it's going to move. Part of the reason it's going to move is because nothing is in its way, but there is a force on it. If I were to go out in this interstellar space where there's essentially no gravity acting on me and just let go of it, it ain't going to go nowhere because there ain't no force acting on it. I'd have to push it or be close to something that would start pulling it in. All right? So it has potential to move when I just hold it above ground. And the reason it has potential to move is because how high it is above ground. It's not on the ground. It's above the ground. And guess what? If I raise it higher, it has more potential to move through that displacement, and it'll also obtain a greater speed. So it seems like the higher that displacement potential is, the more force of impact due to a change in speed being higher or lower depending on how far above the ground I let it go. So this work, this is energy we're dealing with, it's work done on a system. Okay, gravity, if our delta S was vertical, gravity would be working on the object. Okay? This other side of the equation, we like to call this the change in kinetic energy. So we have work it keeps giving me that thing there. and we have kinetic energy, or the change in kinetic energy more explicitly. These are always in balance. You've probably learned from another science class, probably chemistry, you can either, energy can't be created or destroyed, only changed in form. Mass, same thing. Okay, if we were to put a dome over CAC and burn it to the ground, I'm not suggesting that we do that, by the way, and just turn every building and brick into ash, but make it so that none of that stuff can escape, the weight of that system wouldn't change because the mass of that system didn't change. Okay? Even if some of it turned to gas and whatnot. So that would be hard to do, but we've done that on a smaller scale. In fact, the guy that came up with this, Lavoisier, I think his first name was Antoine Lavoisier, a French dude, and he lost his head in the French Revolution. But before he lost his head, he made a lot of contributions to science, especially chemistry, one of them being the idea of conservation of mass. Okay? So, in fact, we'll have a movie at the end of the semester to commemorate all sorts of things in physics and set us up for next semester. All right, so we have this work kinetic energy theorem, all right? And so knowing that W equals the change in kinetic energy and that the formulas for that would be this way is important. So let's apply this something. So let's have an object of some mass above ground. So there's some height above ground that this object has. And initially, its speed is 0 because it's being held in place by something. And then down here at the bottom, right before impact, what will the speed be? Well, by virtue of its position, it has a certain amount of potential energy, okay? And so if I recognize that there's going to be an exchange between the energy that this object has due to its position relative to gravity and the speed that it will obtain right before it comes to a stop, I can deploy this formula. Well, this formula says force times the displacement, which is going to be height in this case, will equal 1/2 the mass of the object times the difference in speed squared. Well, that was 0. So I can drop that minus v0 squared. The force that's on this object is the force of gravity. So that's mgh equals 1/2 mv squared. So the potential energy of the object due to its height is equal to the kinetic energy that it will obtain due to displacement caused by the force of gravity. That would be a English version of what was just written. I hope you recognize that mass is common to both sides of this equation. I can get rid of that 1/2 by multiplying both sides by 2, and I can get that the speed of the object will just be 2 times gravitational acceleration constant times the height of the object. All that really happened there was I took the zeroth law theorem and boiled it down. Mass dropped out. Remember, I added mass into the zeroth law theorem to get work and energy. And then it ends up not mattering with respect to the speed of the object. Now, how many times have you heard that? You know, if I drop 2 things at the same height, you know, are they going to fall at the same rate? And yes, they will fall at the same rate, which means they're going to have the same speed when they fall. All right, so the mass of the object isn't going to make it go faster in free fall. The height of the object will make it go faster. The gravitational constant, if we were, say, in a different location in the universe, meaning we're on Jupiter, whatever little g is for Jupiter, or Mercury, or Mars, or whatever, then yes, I'll have different speeds. But on Earth, little g is 9.81, all right? We'd have to compute it for other places. And so now I can know the speed of the object. So let's say that, just for grins, you know, if h equals 100 meters, then v is going to be the square root of 2, we'll stick with 10 for now. So that's going to be the square root of 2,000, all right? And I should have picked numbers that were easier to deal with. But if I do a quick calculation, so that's 44 meters per second, almost 45 meters per second. So that's cooking. So something dropped from 100 meters, a football field, is going to be going pretty darn fast when it hits the ground. All right, so dropping things off of buildings onto people, not recommended. That could be quite painful. So that is the basics of what's called the work kinetic energy theorem. So this thing is the work kinetic energy theorem. Often we'll just hyphenate that work kinetic thing. And it comes from basically bringing inertia, or the mass of an object, into the zeroth law theorem, which simply describes the motion of the object, both its changing speed and position. So on the Atwood machine, we've already covered forces on this. We need to talk about the energy approach. And so often we'll use a big E for energy. So the sum of all the energies going into a system has to equal the sum of the energies going out, or sum of initial energy equals the sum of final energies. Okay? So initially, in this system, before it's moving, all right, so mass 1, you know, greater than mass 2. So before it's moving, we have initially we have the energy due to height of these objects. Now if I do this, and so I'm going to do this to make it a little bit simpler. So I apologize if you have to erase. Let's put mass 2 on the ground. All right? So initially, there's only one potential energy in the system. And that's the potential energy of the mass that's above ground. The mass on ground has no potential energy. All right? This just simplifies our math a little bit, and it matches what's in your handout. So what I have is I have the work that gravity will do on mass 1. All right? That's what the system has initially. The work that gravity is going to do on the system that it'll do on mass 1, because it's going to get the system moving. But right now, the only reason it's going to move is because of the potential energy of that box above ground. Are we clear on that? That's what the system starts with. The last part of the system's state, at the end of this motion, right before mass 1, or when mass 1 hits the ground, or right before it, basically right at ground level, we're going to have the potential energy that gravity will exert on mass 2. We'll have the kinetic energy of mass 1, and we'll have the kinetic energy of mass 2. Because both boxes will be moving. So this is the snapshot. You always have to do this with the in and the out, the gazintas and the gazatas. That's the way I like to put it. Going into it, it's just the energy associated with mass 1, potential energy. Right at the end, right before that mass hits the ground, when it essentially has no more potential energy, okay, mass 2 will have gained potential energy, and both boxes will have a speed. Same magnitude of speed, because it's connected by the rope. All right? So this is just before impact of mass 1 hitting the ground. All right? Well, if I convert these things to what we saw before, I'm going to have mass times gravity times change in height. This is mass 1. And that's going to be mass 2 times gravity times the change in height. And this is going to be half mass 1 v squared plus 1/2 mass 2 v squared. And the reason why it's just v squared is this is going to be the final speed. The initial speed's no longer part of the consideration. All right? It was 0 anyways, initially. So now I've changed conservation of energy, and by the way, it is conserved, to this. All right? And so we have this equation that we could mess with. And so I can bring the mgy terms together. So I'll have the difference in mass, delta y on the left, and then I'm going to have 1/2 mass 1 mass 2 v squared by simplification. Let's think about this for a second. I've essentially gone back to the work kinetic energy theorem, because if you look at this right here, isn't that just the differential weight force? We sort of, as part of that little analysis we were doing a minute ago, I just have that differential weight force right there times the height. So it's a force times a height, or a force times a distance. That's work. And then I just have, this is a mass. It's a sum of masses, but it's a mass. It's half mv squared. But it's the energy of the whole system, not just a particular object. So energy has some advantages. I can account for lots of things at once in it. So I really just have the work kinetic energy theorem again. And so when you see work equals kinetic energy, every energy is a balance. What goes in has to come out. All right, the gazintas and the gazatas are equal. at least in the universe at large. Okay? Now, some non-conservative forces would be like friction, because heat is involved with friction, and so that heat will transmit to the surroundings. It might leave the system that you're paying attention to, but it goes somewhere. It just doesn't go away. It might leave the system. And so as you can see on your handout, you know, all of this boils down to V equals the square root of 2 times that mass differential fraction, G delta Y. And the forces equation was the same. We got the same answer by means of a force analysis as we did with the energy analysis.